Today we will continue with additional examples of work. Specifically, we will learn how to utilize the ideal gas equation of state to quantify work in various systems. Here we will distinguish two fundamentally different types of processes. One is the isobaric process, which is occurring at a constant pressure, and the other is the isothermal process that is occurring at a constant temperature. We will learn that reversible and irreversible processes exist and what the differences between these two are. In general, be ready for more integrals. As I mentioned previously, this is something that will be with us for quite some time. We will in the future also look at many different types of processes, and we will quantify the heat and the work involved with them, in addition to changes of the internal energy and later also changes of the entropy, and integrations will be a vital component of that. Now let's look at a specific example. We have a piston with an ideal gas inside of it. The ideal gas has a temperature at the beginning and a volume, and the piston has an initial position. The piston itself has an area A, and the pressure inside of that gas is the pressure that is coming from the external pressure, the atmosphere, which is also in this upper part of that piston. It can exchange with the outer atmosphere because this is not airtight. Plus there's an additional pressure that's coming from a weight which is on top of that. So this mass will experience a gravitational force that is pulling it down. A force acting on this area gives us an additional pressure, and that pressure we have in this gas. Now, when we apply heat, we'll quantify these things later, but if we apply heat to the gas, the temperature of the gas will change. And if the temperature increases, the gas wants to expand. And it will, because the pressure that is applied to that gas is always the same one. So if we increase the temperature, the gas will expand. We will see that in the ideal gas law. And that means that it's basically performing work on the environment, and it's working against something. It's working against the force that is exerted by that atmospheric pressure and the force that is exerted by that mass. Now, as mentioned, the pressure during that process, pressure before, the pressure afterwards in the gas, and as well as the pressure during that process is always the same. This is a so-called isobaric expansion or constant pressure expansion. So this is going to be important. It will actually make calculating what is happening here in terms of work a lot easier. So the pressure in this process is the same because the pressure is exerted by the atmosphere and that weight, and that is there before and after and during the process. The gas cylinder expands against this external pressure. If you want to quantify that external pressure, this is total external pressure. This is P, and P is the atmospheric pressure over here, plus the additional pressure that is coming from the mass. The mass is pulled down with a force, which is the gravitational force, which is m times g. We learned that before. We divide that by the area of a piston. A force divided by an area is a pressure. So this is the total pressure in that system. Now we assume that the gas inside of a cylinder is ideal, so at the same time, this equation, the ideal gas law, must be valid. That total pressure is also the amount of substance, the amount of gas molecules, times the gas constant, times the temperature, divided by the volume. Now, if we solve that equation for the volume, we already see that if we change the temperature of the gas and the pressure remains constant, and the volume has to increase. This is a direct consequence of that. So we already see just from the ideal gas law that if the pressure remains constant but we are changing the temperature, the volume has to increase. Because the amount of substance and the gas constant, they are not changing, they are the same. Now, we already know that in order to calculate the work, we have to basically describe what is the force that we are working against. And that is relatively simple. We have this total pressure that is coming from the environment, that is pushing on that gas, and creates a pressure of that gas, and it's acting on this area A, the area of that piston. So if we multiply both, we get the force that is acting on that gas. And this is the force that we have to work against if we want to expand the gas. Now the force that we have to exert for that, we learned that as well. We called it previously F prime. It's exactly the negative of that. So this is minus F or minus P times A. And that force, because the pressure is constant in the whole process, The area of the piston remains constant as well. The force is constant too. We then go to our general work equation, where we have a force and we have to integrate that force over a path. Basically what is happening. In this case, this is a piston that is moving from the position H0 to the position H1. Well, that makes it relatively easy for us, because if the force that we are applying is constant, we can put it in front of the integral, and that makes the whole thing pretty easy. And we integrate only dh from H0 to H1. This is H1 minus H0, so this is the change in the height of the piston. And if we now plug in what this force that we are using is actually, how that is described mathematically, this is the negative pressure times the area of the piston, and the area of the piston times the change in the height of the piston. Well, this is nothing else but the change in volume. So A times H1 minus A times H0. This is also V1 minus V0, so the difference in the two volumes, or delta V. So the work that we are now exerting on the environment is minus P times delta V. So the minus the pressure of that gas, which is pressure is coming from the environment, is pushing on that gas, times delta V. Now what you might notice is that using that definition of what is the force that we are working against, what is the force that we are using to do that, we already get the right sign for the work. So we get, because pressures and this change, pressures are positive and the change of the volume is also positive, we get here a negative number, so the work is negative. And this is what we expect from the self-worth system sign convention. The system is performing work on the environment. So it is losing some energy because it is working on the environment. And the work that we calculate should be negative. And if we set it up correctly, we actually get that out automatically. But always double check. Think about the selfish sign convention for the system. The system is selfish if the system is performing work. That work we describe as negative. So if you didn't set it up right and you get a positive number, then you know that there's something wrong. And in the best case, you just have to flip the sign. But be always aware of that. Now, we saw that in the end, everything reduced to this P times delta V. Don't just use that equation without thinking, but it's an isobaric process. It's an isobaric expansion. But we also learned that volume work problems we can also express with this equation, which is a simpler version. We don't have to go back to, okay, what is the force? And the force is acting over a distance, but we can also use this equation where we're using a pressure, and the pressure is acting over a volume change. So we're integrating the pressure over a change in volume from V0 to V1, and we end up with exactly the same result. So you will most likely find this a bit more convenient for future problems, whenever there is a volume change included. Now let's have a look at a slightly different process, where we have our gas, but we added stoppers. Stoppers that prevent the piston from moving at all. And now we apply heat and change the temperature of the gas. And the question is now, in this situation, how much work will be performed when we heat up the gas? Now think again how work is defined. These are the two solutions, possible solutions, and only one is correct. One, the piston doesn't move and no work is performed. So the work is zero. We're heating up the gas, but there's no work performed. This one, number B, pressure builds up in the cylinder, which means we apply work, but it can't be calculated with that equation. It's something else. It's not the work as we know it from the calculations, where we have a force, and the force needs to be integrated over a change in, for example, position of that piston. It's something else, but there is work implied. So what is correct? Only one of these statements is correct. Take a few seconds and come back once you know what's happening here. Okay, I hope you all arrived at the same conclusion, that in this case the piston is not moving and we are heating up the gas. There will be an additional force from the gas because it wants to expand, but it cannot. But as long as nothing moves, no work is performed. So if there's no movement involved, work does not take place. So the answer is A. The work is zero, no work. Now we will look at a different type of process. Here again we have a piston with a gas inside of it. We see that in this particular process we are compressing the gas, but the main difference to the isobaric process that we looked at before is that in this case we're doing it at constant temperature. This is ensured through thermal contact with this big plate beyond it. We assume that this is basically infinitely large, and whatever heat we take out of it or put into it, the heat of that, the temperature of that environment essentially of that plate does not change. Now we are exerting a force on our gas in order to compress it. That usually would change the temperature of a gas. We will see that later from the ideal gas law, but we do it very slowly and we allow for heat exchange with the environment. So while we're doing it, we do it slow enough to ensure that the temperature in the gas is remained constant, because we are allowing heat exchange with the environment. Now the position of the piston again changes from position H0 to H1, and we're reducing our volume from V0 to V1. Now, as mentioned, the special part about that process is that it is isothermal, meaning that the temperature of the gas remains constant all the time. This is only possible because of that constant exchange of heat with the environment, so this would not work with an isolated system, of course. We need to have an exchange of heat. The gas cylinder is compressed by an external force against the internal pressure of the gas. So there's now work performed against the pressure of the gas itself. We assume that the gas inside of the cylinder is ideal, that pressure is N times R times T divided by V, this is just the ideal gas law, and that is N times R times T divided by, well, the volume is nothing else but the area of the piston times the height. So this is the pressure that is inside of the gas, and this is what is worked against upon, but not by the system. This is now worked against upon by the environment. The internal pressure in this case will not remain constant while the volume changes. This is the important part. So here the temperature of the system remains constant, but the pressure is not. This is what distinguishes it from the previous isobaric process. What is an important part here, and we will see that in the end of the lesson, is that the compression is performed reversibly. That means it's done slow enough that the temperature is maintained constant, that there is always permanent heat exchange. So the force that we apply, we will do it very, very slowly. We use just as much force as we need in order to do the compression, and we will adjust the force accordingly because we will need more and more force the further we compress. We will see that in a second. The movement of the piston occurs essentially in infinitesimally small changes, and all this ensures that while we are compressing the gas, as said, if we would do it very fast, or if we would not allow for heat exchange with the environment, the temperature would change. That's something we don't want. We want the temperature to be constant all the time, so we do it very, very slowly so that the temperature remains constant because we allow for this heat exchange with the environment, which of course takes a little bit of time. So this is what we call a reversible process, because we're just using as much force as needed to just very, very slowly move the piston. And we adjust the force as needed to maintain that movement, but we do it as slow as possible. This is called reversible. Now to compute the work, we are now using the volume work equation. So this is making our life a little bit easier now. We have a change in volume, we have a pressure, but we already saw here the pressure is not constant, so we cannot put the pressure in front of the integral. Instead, we have to replace the pressure by this expression here in terms of the ideal gas law. So the ideal gas law contains a few things that we know are constant, which is the amount of substance, the gas constant, the temperature remains constant, that is the whole point of that process, but the volume does not. So we end up with that slightly modified equation here. So this is the amount of substance R, the gas constant R, the temperature T, and now we're integrating over 1 over the volume from V0 to V1. So that integral is essentially the integral of 1 over x, dx, and that is the logarithm of the volume. So this is this is basically something you would look up in the logarithm in the integration table. We mentioned this example of an integral in the very, very first lesson. So here this is what pops up. And As I said, these integrals, actually this particular integral will show up many, many times in this entire course. So be aware of that. So when we integrate, we have the amount of substance, the gas constant, the temperature, and now we have this logarithm, the natural logarithm to be precise, of a volume, and in the limits of V0 and V1. So if we plug that in, then we have n minus n times r times t, the logarithm of V1 minus the logarithm of V0, and if you remember your logarithm rule, if we subtract one logarithm from another, then this is just the logarithm of the ratio of the arguments. So this is minus n times r times t times the logarithm of the ratio of V1 and V0. If you look at that, if V1 is smaller than the initial volume V0, then this ratio will be smaller than 1. The natural logarithm of anything which is smaller than 1 is negative. So we have another minus sign over here, minus nRT times this negative result, which is coming from that logarithm. Minus times minus is plus. So the work that is performed on the system is positive. W is greater than 0. In this case, the environment is performing work on the system. So the system's energy goes up because there's work performed on it, and the work should be positive. And again, if we set it up correctly, that actually comes out of the equation. But as I mentioned previously, for the isobaric case, think of that sign convention, see what you get out, and if it's wrong, then you might have done something slightly wrong. And in the ideal case, you just have to flip the sign, but basically make this double check. We can arrive at the same result in an alternative way. In the previous slide, we used the equation for the volume work, where we integrate over the pressure over a volume change. What we can also do is we can formulate the same thing via force. It's an equivalent expression. When you think about the force that we need to exert, which is the opposite of the force that we are working against, or we are working against the pressure of our system, which we want to compress. So it's the force that you have to exert is minus P times A, where A is the cross-section of that piston. And if you now substitute for the pressure P, the ideal gas expression, specifically one where we substitute the volume by, or the volume of that piston, of that cylinder, which is the cross-section times the height of that piston, A times H, then we arrive at this equation over here. So it's minus n times r times t divided by A times H times A. So we see that the A actually cancels out. So we don't even need to know what the cross-section of the piston is. We didn't need it in the previous case, and we don't need it here. And we arrive at minus n times r times t over H. This is the force that we have to work against. And it doesn't stay constant while we are compressing it, while H is changing. So we have to take this integration more seriously. So this force that we have over here, that we have to integrate over a change of H, that is not constant. We have to use the actual expression for that. While the n times r times t, that stays constant, so we can put that in front of the integral. The minus, of course, as well, but then we have 1 over h dh, which we have to integrate over. The rest of the equation looks very, very similar. There we have minus nRT times the logarithm of h in the limits of h0 and h1. We do the same as before, and in the end we arrive at minus n times r times t times the logarithm of the ratio of h1 and h0. So this looks a little bit different than the previous result, but this ratio here, if you multiply with a on both sides of the denominator, so up here and down here, then we get actually our volume again. So this is exactly the same thing. There's a different way to formulate that. Probably the volume work expression where we integrate the pressure over a change of the volume, that is a bit more straightforward, but as you can see here, it is completely irrelevant how you do it. So physics doesn't care. As long as all the assumptions are correct and the equations are correct, you get exactly the same result. Now let us briefly revisit what the word reversible exactly means. Changes are employed in infinitesimally small steps. So this is what we also used in this isothermal compression on the previous slide. We basically compress the system in very, very small steps, and that allowed the system to remain in equilibrium at all times. That means that we allowed for the heat exchange with the environment to ensure that we always have an exactly constant temperature. If we do it like that, the process can also be stopped and reversed at all times. And the consequence of all this reversible process in many, many small, infinitesimally small steps is that we optimize the amount of work. That means that we need to apply a minimum amount of work in order to compress the system. If the system would perform work in an expansion, that also would mean that the system can perform the maximum amount of work. So it's an optimization of the amount of work. We can look at these graphs in order to figure out what exactly that means. So this is the piston position down here on the x-axis. On the y-axis we have the compression force, the force that we need to apply, and we start here. This is the original position of the piston, and now we are compressing the system, so we're moving it basically in this direction on the x-axis, and this is the force that you need to apply in order to do that. This is just a consequence of the ideal gas law. It becomes larger and larger and larger the more I compress the system, and if we integrate over that, well, this is exactly the area under this curve, and this is what this integral does. So you can see this is basically the ideal case. Now, this is the reversible case, and if we go to the irreversible case, well, now we start also here, but we apply a force which is larger than necessary. So we overshoot a bit with the force. We make a step until we hit the point where that force is basically not sufficient anymore to compress a system, because that changes while we're compressing it, of course. And then again, we use a larger force, but we overshoot and we do it in these steps. So the amount of work that we kind of apply to the system is now the area under these steps. And as you can see, this is larger than the reversible work. So here we are using more work in order to compress the system than is actually necessary. We do it too fast, we apply too much force. And this is mainly the main difference between reversible and irreversible work. Now let's have a look at the different types of work that we learned about. We learned that work is generally an integral over a force over the distance. So here we have a force, and the variable x in this case changes from x0 to x1, and we have to integrate over that. The force may stay constant, or the force may change while this is happening. This integral doesn't care, we just have to evaluate it correctly. And in this case, F prime that we're using here is the force that actually performs the work. We defined it usually as the opposite of the force that we are working against. So you have to get your definitions right, otherwise you will have a wrong sign. We also learned about volume work, where we are integrating a pressure over a volume change. We saw that this is equivalent, that we can always reformulate it, but sometimes it's easier to use this equation. And the pressure P is the pressure that we work against, and this is why there's a minus over here. And we had a specific example of an isobaric process, which is a simple case because in this case the pressure that we work against is always constant. And that means that we can put it in front of the integral, and in the end what we get is just minus P times delta V. The other process that we talked about is the isothermal process. And in this case it's a little bit more complicated because now the pressure doesn't necessarily stay constant. Isobaric up here, that basically implies that pressure is constant. In an isothermal process that is not necessarily the case. And if we want to calculate this integral, we need to be able to express how the pressure changes while we are changing the volume. And in general we are not always able to do that, but we are able to do that, for example, for an ideal gas. So now we have the pressure as a function of the volume, and well, this is what the ideal gas equation tells us. The pressure of a system depends on volume like this. We have an amount of particles, or the number of moles. We have a gas constant, the temperature, which in this case stays constant for an isothermal process, but then divided by the volume. So this gives us a relationship between the pressure and the volume, and this is what we have to integrate over. And when we do that, we end up with an equation that looks like that. We went through these individual steps, but in the end we have an integral over 1 over v, and that is simply the logarithm. So if we change the volume from v0 to v1, we end up with the work that is performed, which is minus n times the gas constant times the temperature, times the logarithm of the ratio of these volumes. Final volume divided by the initial volume. Now my general recommendation for working with these equations is to learn how to start from these basic equations for the calculation of the work. For example, integrating over a force over a change of some variable, for example x, or a height of a piston, or integrating a pressure or a change of a volume, and then to adapt the equation to the particular process that you're studying. For example, an isobaric process where this integration becomes quite trivial, or an isothermal process where it becomes a little bit harder. We have to express the pressure as a function of the volume that we're changing, and then we have to calculate the corresponding integrals, which are essentially always the same ones. We'll have a lot of integrals of 1 over something, like 1 over the volume, which gives us a logarithm. The mathematical steps will always be very, very similar, but they can be applied to many, many different cases. The alternative would be to memorize the final results, these final equations. For an isobaric process, we have the pressure times the change in volume. For an isothermal process, we have change in volume at constant temperature, and in the end we have this logarithm over here of a ratio of the different volumes. Of course, this can all be memorized as well and be applied, but this is only the beginning. We will have many, many, many more equations, and all of them will look quite similar, and it's very easy to get confused. This could be a problem. For some people it works quite well, but I strongly recommend to learn how to do these individual steps and to use that. You will usually have enough time to do that, and it's actually way more general than that. So this is relevant not only for this class, but these basic equations, they don't only appear in physical chemistry, they appear in many other contexts as well. And doing these individual steps is a very, very general skill that can help you in many other cases as well. Now, what did we learn today? We learned how to use the ideal gas equation of state to quantify work. Particularly, we learned how to distinguish two fundamentally different types of processes: the isobaric process at constant pressure and the isothermal process at constant temperature. And we learned about the difference between reversible and irreversible processes. We have reversible processes that are done with small, infinitesimally small steps, which are optimizing work. So it minimizes the amount of work that you have to apply to a system in order to change its state. And it also maximizes the amount of work that the system can actually perform. At this point, you might wonder why you're learning so much about ideal gases and cylinders and pistons and changes in volume if the title of the class is Physical Chemistry with a Biological Focus. So where is the biological focus in these examples? Well, the key point is that what we learn about work and later also about heat is absolutely general. This is why I put so much emphasis also on your ability to use the general equations, integration of a force over change in distance, integration of a pressure over change in volume, to calculate, for example, the work, because this applies everywhere. The ideal gas is a nice example because here we actually can express the pressure as a function of a volume and the temperature and the amount of substance, and we can perform these calculations directly. For anything more complicated, like a real biomolecular systems, we are usually not able to do that with simple means. However, work plays a big role also in biomolecular processes. And whenever that is the case, usually motor proteins are involved. Here you find an example. You see here microtubuli. These are parts of the cytoskeleton, and they're usually starting around the nucleus and are ending at close to the cellular membrane. And they're basically highways that go through the cell and are used for transport. You see here a relatively large vesicle, and this is going to be transported by this motor protein, in this case kinesin, which walks along the microtubuli and is basically exerting a force on that vesicle to transport it through a cell in a directed way. This is all driven by ATP hydrolysis. This is a reaction that we'll talk a lot about in this class. So ATP with water becomes ADP plus phosphate, so one of the phosphates is basically split off. And let's now have a look on what that looks like in this animation, which is of course an artistic representation of what is going on. But what we can see here is that these motor proteins, they have little feet that allow them to work and to walk along the microtubuli. They are exerting a so-called power stroke, which is basically creating the force that is then exerted on the vesicle in order to move it. And you can see that there's a force applied, something is moving, so you can see what work is at play. In this colorful microscopic image, we can see how these different parts of the cytoskeleton, particularly the microtubuli and also the actin filaments, which is a different part of the cytoskeleton, how they are arranged inside of a cell. This is an image of an entire cell. We see the nucleus in the middle. We see that the microtubuli originate around the nucleus, and then they basically elongate towards the cell membrane. And we see the actin filaments, which are basically going in the opposite direction, or not opposite direction, but perpendicular direction, they basically circumference the cell. Now, there are different types of motor proteins which are transporting things along these different types of the cytoskeleton. Cytoskeleton itself is formed by different types of proteins, the microtubules by tubulins and the actin filaments by actin. Kinesin and dynein are two proteins which are, as you saw in the movie, moving along the microtubule and can transport things in microtubule. The kinesin is usually walking away from the nucleus towards the outside of the cell. The dyneins are doing the opposite. Actin filaments are essentially the walkways or highways for myosin, so they are walking along actin filaments, and this is also what happens in your muscle cells when they contract. This involves actin filaments and myosin molecules which are exerting a force on the actin filaments, and this is what makes your muscles contract in the end and allows you to perform work. So as you can see, there are many examples also in biology and in biochemistry where work is at play, usually in the form of motor proteins performing this work, and all of this is driven by chemistry, as we will learn. But the fundamental ideas of work and heat, and there's actually a lot more that we have to learn about thermodynamics in terms of fully understanding how we can optimize the amount of work that we can perform given a certain amount of energy in some form. This is basically the content of this class. So there's a lot more to follow, but we will often use simple examples and simple systems like ideal gases, but we will usually come back towards the biomolecular context that this can be applied.